Welcome to the calm unknown. Tonight, we explore a quiet mystery that shapes how we see the world. The universe is vast, and much of it remains hidden, not because it isn't there, but because it's just beyond what we understand. Let's begin. Imagine descending slowly through layers of darkness, deeper and deeper toward the hidden heart of the Milky Way. 26,000 light-years separate us from that distant point, a journey veiled by thick curtains of dust that have guarded the secret for countless ages. At the exact center waits something extraordinary, a supermassive black hole known as Sagittarius A. It carries the mass of 4 million suns compressed into a region smaller than our solar system. In nearly every other large galaxy we observe, similar monsters feed greedily. Gas spirals inward, compresses, heats to millions of degrees, and blazes with light bright enough to outshine entire star collections. These active nuclei announce their presence across vast distances, yet our own black hole remains almost silent. Only faint, occasional whispers escape. Brief flickers in radio waves, subtle infrared glows, rare X-ray echoes. Theory insists it should feast steadily. Dense clouds of gas drift nearby. Massive stars die violently in the neighborhood, scattering material. Gravity should draw streams inward continuously. But Sagittarius A emits mere fractions of the expected radiance, thousands of times dimmer than counterparts elsewhere. The discovery unfolded gradually. In the 1930s, Carl Jansky detected mysterious radio hiss from the galactic plane. Decades later, astronomers pinpointed a compact source in Sagittarius and named it Sagittarius A. By the 1970s, evidence mounted for an enormous invisible mass. Stellar orbits traced perfect rosettes around an unseen point, moving at percentages of light speed, confirming something extraordinary lurked there. In 2022, the Event Horizon Telescope delivered humanity's first direct portrait. A dark shadow encircled by a faint, glowing ring. The silhouette of the event horizon itself, light bent by gravity's extreme curve. Stars near this shadow whip along elliptical paths like petals caught in an invisible whirlwind. Their speeds reach over 3% the speed of light at closest approach, yet the black hole barely notices. It flickers only rarely, brief brightenings lasting weeks or months, then returns to darkness. A monster 4 million times heavier than the sun sits at our galaxy's core, and it is strangely, almost deliberately, starving. What holds back the feast? Abundant gas swirls within reach. Tidal forces should shred clouds and deliver material. Magnetic fields might arrest inflow, or low spin reduce efficiency. Perhaps past activity cleared the inner regions, leaving little to consume today. Quiet questions linger. Why this restraint when others gorge? What invisible barrier intervenes? The galaxy seems to guard the answer patiently, as if the black hole's hunger, or lack of it, shapes everything around it. If this starving giant once devoured greedily, what colossal scars might its ancient meals have left, rising above and below the galactic plane? Draw closer now to the immediate surroundings, a turbulent realm mere light days from the event horizon. Here, hot gas collides in chaotic streams. Massive stars cluster densely, burning briefly and brightly. Magnetic storms twist through the plasma. Reservoirs of material orbit perilously near the point of no return. Yet almost nothing crosses the boundary. Tidal forces at these distances should stretch and shred anything loose, funneling debris inward. Gravity demands a steady diet, but the black hole accepts only occasional morsels, small clouds perhaps, or tidally disrupted stars slipping in quietly. Recent observations track these rare events with exquisite care. Chandra catches faint X-ray echoes when material briefly heats. Gravity at the Very Large Telescope follows infrared flares, watching dust glow as it compresses and accelerates. Radio telescopes record variability, hinting at sudden inflows. Each flare lasts months, brightens modestly, then fades. The black hole returns to quiescence, as if satisfied with mere tastes. This black hole has enough nearby food to shine like a beacon across the universe. Yet it chooses darkness. Compare it to active nuclei elsewhere, quasars blazing with the light of trillions of suns, powered by voracious accretion. Our center glows thousands of times fainter than expected for its mass and surroundings. The anomaly deepens with every new measurement. Proposed barriers emerge slowly. Powerful magnetic fields might thread the gas, resisting collapse like invisible scaffolding. The black hole's spin could be low, reducing the efficiency of drawing material inward. Or past feedback, enormous outflows long ago, may have evacuated the inner sanctum, leaving sparse pickings today. Orbiting stars serve as precise probes. The S-cluster members trace tight paths around the darkness, their motions confirming the mass, yet revealing no strong disturbance from ongoing feeding. They move like dancers around a still center, undisturbed by major disruption. Could the restraint be temporary? Rare brightening events, observed in 2019, 2022, and more recently, suggest occasional larger meals. What triggers them remains unclear. A passing cloud? A disrupted star? The black hole waits patiently, accepting only what comes easily. The implications ripple outward. In more active galaxies, relentless feeding drives powerful winds that reshape entire structures, expelling gas and quenching star formation. Our milder case allows different balances to persist, perhaps permitting features that violent feeding would erase. The deliberate hunger shapes the environment profoundly. It permits chaos nearby, without constant upheaval. It leaves room for other energies to escape unchecked. That deliberate hunger may have allowed enormous energies to escape outward instead, inflating vast cavities that tower over the entire galactic disk. Step back gradually from the event horizon's edge and contemplate the larger pattern. In distant galaxies, active black holes often drive regulatory cycles. Relentless feeding heats surrounding gas, launches winds that expel material, and eventually starves the center temporarily, a feedback loop maintaining balance over cosmic time. More violent phases alternate with calmer ones, shaping evolution. Our case appears exceptionally mild. The black hole's quiescence stretches longer than typical, its flares weaker and rarer. Recent studies through 2025 and early 2026 refine flare statistics and faint accretion signatures, confirming episodic rather than continuous behavior. Brief tastes separated by long fasts. This restraint permits other imbalances to endure. Nearby gas reserves remain largely undisturbed. Massive stars form and die without constant disruption from powerful outflows. The inner galaxy maintains dense conditions that a more active nucleus might clear. A more gluttonous center could alter everything. Stronger winds might expel vast gas quantities, quenching star formation across wide regions. Radiation and jets could sterilize zones, disrupting chemistry needed for complex molecules or planetary systems. The Milky Way might appear barren or distorted, perhaps lifeless. If our central black hole ate like its cousins elsewhere, the Milky Way might be a very different, perhaps lifeless, place. Statistical comparisons sharpen the anomaly. Among observed supermassive black holes of similar mass, few remain as quiet given comparable surroundings. The Milky Way emerges as an outlier, its center unusually restrained, possibly rare. This calm may trace to past episodes. Ancient outbursts, powerful enough to inflate enormous structures, could have cleared inner regions long ago, leaving sparse material today. The black hole fasts as consequence of earlier gluttony. Personal resonance grows. The same restraint that puzzles astronomers may have enabled stable conditions elsewhere: moderate star formation, preserved gas reservoirs, protected zones where planets form undisturbed. Cosmic violence tempered just enough to allow fragile complexity. The starving giant sits at the gateway to stranger features. Its deliberate darkness permits energies to escape differently, not trapped in accretion glow, but released in other forms that sculpt the galaxy subtly. As we withdraw from the starving giant's doorstep, two symmetrical voids emerge, enormous bubbles inflated by energy no ordinary process should produce on such scale. As we withdraw from the starving giant's doorstep, two symmetrical voids emerge, enormous bubbles inflated by energy no ordinary process should produce on such scale. Shift your gaze now to the highest energies the universe emits, gamma rays, born from the most violent events and fastest particles. In this invisible light, the galactic center reveals something astonishing. In 2010, astronomers sifting through data from the Fermi Gamma Ray Space Telescope stumbled upon two vast, symmetrical lobes. They rise perpendicular to the galactic disk, one above the plane, one below, perfectly mirrored like reflections in still water. Each lobe stretches more than 25,000 light-years from the center, half the height of the entire visible Milky Way. Their boundaries appear remarkably sharp, almost sculpted. Their volume is staggering, large enough to swallow thousands of smaller galaxies whole. Yet in ordinary starlight, they are nearly transparent. Dust obscures little. for there is little too obscure. Stars do not trace their outlines. Gas within is thin and hot. They exist as cavities carved from the halo, outlined only by the faint glow of particles accelerated to near light speed. The discovery was pure accident. Researchers mapped known sources of cosmic rays interacting with interstellar material. After subtracting everything expected, these giant silhouettes remained, staring from the data for years, unnoticed. No earlier telescope combined the wide field and sensitivity to catch them. No model predicted such structures. Their symmetry is exquisite, centered precisely on Sagittarius A. Their edges crisp, not diffuse as gradual leakage would produce. Two colossal voids, big enough to engulf thousands of star systems, rise silently from our galaxy's heart. And no one noticed them until 2010. Imagine them as ethereal sculptures, ghostly balloons inflated from within, their surfaces shimmering in light no human eye perceives. Particles crash into rare gas along the boundaries, producing the gamma glow we detect. The interiors reach millions of degrees, threaded with magnetic fields and cosmic rays. The timescale challenges understanding. Estimates place their age at a few to 10 million years, recent in cosmic terms. Whatever created them acted swiftly, releasing energy focused and directed. Stand beneath a dark sky and face the galactic center. The familiar band of the Milky Way arcs overhead. But high above and below that band, invisible, these colossal cavities tower, silent witnesses to an event that shook the galaxy, yet left barely a ripple in visible light. They are not the gentle expansion of ordinary stellar winds. They are not the slow diffusion of ancient supernovae. Their scale and sharpness demand something extraordinary, a sudden, powerful release that punched through the disk and inflated these voids before momentum faded. These ghostly cavities are not truly empty. Traces of unimaginable violence linger within. The Fermi bubbles contain more than emptiness. Hot plasma fills their interiors, magnetized and alive with the universe's fastest particles. But how were they born? Two main stories compete for explanation, each compelling yet incomplete. The first returns us to the black hole. In other galaxies, active nuclei launch powerful jets, twin beams along the spin axis, driven by matter spiraling inward. Our Sagittarius A is quiet today, but a few million years ago it may have awakened briefly. A large gas cloud or disrupted star cluster falling in could have triggered intense accretion. As material crossed the event horizon, enormous energy released in jets perpendicular to the disk, punching outward, heating gas, accelerating particles, inflating the bubbles rapidly. This scenario fits the symmetry perfectly. The lobes align with the galactic center, centered on the black hole. Their sharp edges suggest a short, explosive phase rather than gradual buildup. The energy budget matches roughly, equivalent to millions of supernova explosions focused over centuries or millennia. The second story blames stars. The central molecular zone packs dense gas reserves. In the past, rapid collapse collapse may have birthed thousands of massive stars in a concentrated burst. These stars live briefly, die violently, their supernovae and winds combining into a superwind that drove outwards steadily, inflating the cavities over longer periods. This stellar explanation appeals because we see evidence of recent massive star formation near the center. The required energy is plausible if coordinated, yet it struggles with the exquisite symmetry and precise alignment. Recent observations complicate both tales beautifully. The Rosetta X-ray telescope, through all sky surveys completed by 2025, mapped hotter interiors with greater clarity. Edges match gamma-ray boundaries almost exactly, but faint extensions appear. Older, cooler shells surrounding the bright lobes, suggesting multiple inflation phases. Perhaps an earlier, larger outburst overlaid by a more recent one. Embedded within the million-degree plasma, astronomers found dense cold clouds, surviving where they should evaporate instantly. Some fall back toward the disk at high speed, like rain from a furnace. Their presence hints at continuous replenishment or complex cooling. Microwave haze from Planck data follows the same shape subtly. Polarized radio emission traces magnetic fields draped along the surfaces. A deeper twist emerges. The bubble's sharpness and alignment challenge both models equally. Jets should produce narrower collimated features initially. Stellar winds should diffuse more softly. Multiple phases, black hole flare combined with sustained stellar activity, may be needed. The force that created these bubbles was powerful enough to reshape half the galaxy, yet left almost no trace in visible light. The energy released rivals the output of entire active galaxies over brief periods, focused here into bipolar outflows. Particles accelerated within still produce the gamma glow today, frozen echoes of ancient violence. The bubbles remind us the Milky Way remains dynamic. An event recent enough to preserve sharp boundaries reshaped the halo profoundly. Cosmic rays injected then still propagate, perhaps reaching Earth as part of our background radiation. The debate continues actively. Improved Fermi data and multi-wavelength correlations through early 2026 slightly favor episodic black hole activity. But stellar contributions cannot be ruled out. Perhaps the truth blends both. The black hole's past awakening, amplified by central starburst. Whatever the origin, the bubbles stand as testament to power released differently, because the center feeds so sparingly today. As astronomers probe the bubble's origins, a softer anomaly glows at their base, extra light that refuses to match any expected source. Before ascending fully into the bubble's vast heights, linger at their roots where they meet the galactic plane. The same Fermi telescope that unveiled the colossal lobes detected another signal, gentler, more diffuse, yet equally stubborn. A broad excess of gamma rays concentrates toward the inner few thousand light-years, peaking at the center but extending outward in a roughly spherical haze. This glow nestles precisely where the bubbles emerge, sharing the crowded heart. Known processes, cosmic rays striking gas, pulsar beams, supernova remnants, have been modeled meticulously and subtracted. Yet surplus remains. Its spectrum peaked softly, its distribution more bulbous than the flattened stellar bulge. This phantom light has been chased for years, its implications profound. Right where the bubbles root into the center shines a phantom light scientists have chased for years. The excess overlaps spatially with bubble bases and central filaments. Past activity, whatever inflated the cavities, may have injected conditions for both. Cosmic rays filling the lobes while creating environments for the glow. If the black hole flared dramatically, it could have accelerated particles contributing to both features. If stellar superwind dominated, the same supernovae might have left rich pulsar populations or altered gas distributions. The black hole's restraint ties everything together delicately. In more active galaxies, constant feeding might trap energy in accretion glow, preventing such focused outflows. Here, sparse inflow allows occasional larger events to release energy differently, sculpting bubbles, perhaps seeding the excess. The center hosts layered anomalies, underfeeding permitting outbursts, outbursts carving cavities, cavities framing unexplained light. Each defies simple expectation, yet coexists in fragile balance. Recent correlations sharpen connections. X-ray features from Aeroseta align with gamma edges. Cold clouds falling through bubbles may trace material cycles linking center to halo. The hypnotic web forms, the starving giants' past meals escaping as bubbles, their echoes perhaps mingling with the phantom glow. The galaxy breathes slowly, inhaling gas sparingly, exhaling occasionally in vast, structured sighs. This unexplained glow may betray dark matter's presence, or hide an army of spinning corpses no one counted on. This unexplained glow may betray dark matter's presence, or hide an army of spinning corpses no one counted on. Return once more to the crowded inner galaxy, where the colossal bubbles root into the plane, and the starving black hole waits in darkness. Here, in the same high-energy light that revealed the vast cavities, a subtler signal persists, softer, more diffuse, yet impossible to erase. Astronomers call it the galactic center gamma-ray excess. It appears as a gentle, spherical haze of gamma rays, the universe's highest energy photons, concentrated toward the inner few thousand light-years. The glow peaks brightly near Sagittarius A, then fades gradually outward, more rounded and bulbous than the flattened distribution of stars and gas in the bulge. To isolate it, researchers perform meticulous subtraction. They model every known contributor. Cosmic rays slamming into interstellar clouds, producing secondary gamma rays, supernova remnants accelerating particles, millisecond pulsars beaming emission, even starlight scattered to higher energies by fast electrons. Layer by layer, these expected sources are removed, yet a stubborn surplus remains, a faint whisper refusing to vanish. Its spectrum curves broadly, peaking around a few billion electron volts before trailing off. Its spatial pattern centers almost perfectly on the black hole, extending in a rough sphere, rather than following the disk or bar. First hints emerged in 2009 as Fermi data accumulated. Through the 2010s, the signal strengthened with better calibrations, sparking intense debate. Refined analyses in the 2020s, incorporating multi-wavelength constraints, confirmed its persistence. As of early 2026, the excess endures, weakened slightly by resolved sources but never fully explained. At the galaxy's heart glows extra light in the universe's highest energies. Light that may reveal dark matter or expose a vast hidden population no one anticipated. The match to one possibility is tantalizing. Dark matter, the invisible substance dominating cosmic gravity, may consist of particles that interact weakly. In the dense inner galaxy, where dark matter should concentrate strongly under the gravitational pull, these particles could occasionally meet and annihilate, converting mass directly into gamma rays. Many theoretical models predict exactly this: a broad spectral peak, a spherical distribution centered on the galaxy's heart. The observed excess aligns remarkably well with particles in the tens of GeV range, a mass scale favored by some extensions beyond the standard model. The pattern is almost too symmetrical, too perfectly centered. Challenging explanations tied to ordinary stars or gas, which follow the bulge's slight offset and flattening. If this is dark matter's fingerprint, why so ambiguous? Why does the signal persist despite ever better subtractions and resolved point sources? The tension builds quietly, a detection that could rewrite physics, yet refuses clear confirmation. The excitement is tempered by caution. The inner galaxy is crowded, backgrounds complex. Subtle systematic effects in instrument response or modeling could mimic the surplus. Multi-wavelength checks, infrared source counts, radio pulsar surveys constrain but do not eliminate the signal. The audience senses the detective story unfolding, a clue that promises profound revelation, yet demands patience. The glow hovers at the edge of understanding, whispering possibilities without shouting answers. While many chase exotic particles for this phantom light, a growing case points to thousands of spinning remnants camouflaged in the crowd. The conventional challenger has gained ground steadily. Not new physics, but an overlooked population of ordinary objects. Millisecond pulsars, ancient neutron stars revived to extraordinary spin by stealing matter from companions long ago, now tick hundreds of times per second. Their powerful magnetic fields accelerate particles into beams that sweep across space like cosmic lighthouses, emitting across wavelengths including gamma rays. Individually faint, thousands scattered through the bulge could collectively produce a smooth extended glow mimicking the excess perfectly. Quiet retirees hidden in the stellar crowd, their combined whispers adding up to the stubborn surplus. Radio surveys with telescopes like Meerkat and the square-kilometer array precursors have uncovered dozens in the central region, with hints of hundreds or thousands still unresolved against bright backgrounds. Their luminosity, scaled up, approaches the excess level. The spectral match is close, broad peaks from summed pulsar curves aligning with the observed bump. Morphological extensions in recent analyses show faint traces following the bar or bulge, consistent with old stellar distributions. Refined Fermi data through 2025 to 2026 reveal subtle mismatches for pure dark matter. The excess softens at higher energies more than simple annihilation predicts. Faint time variability emerges, marginal but suggestive of individual pulsar flaring. Morphological refinements show the glow slightly less spherical, with elongations favoring stellar tracers. Thousands of dead stars may be ticking in perfect unison to produce this glow, but their arrangement is suspiciously ideal. The bulbous symmetry remains puzzling. Millisecond pulsars should trace the stellar bulge, slightly flattened, offset from the exact center. Yet the excess clings stubbornly to spherical perfection, centered on the black hole. We have not resolved nearly enough individual sources to account for the full brightness, though many may hide in confusion or faintness. Deep radio searches continue, promising resolution. Hybrid possibilities intrigue. A dominant pulsar population overlaid on a weaker dark matter base. The spherical core from annihilation, extensions from stars, or unresolved point sources of other kinds contributing. The implications hang in balance. Pulsar dominance would reveal overlooked stellar evolution in dense environments, binary disruptions, recycling, survival in the harsh center. Dark matter confirmation would open new physics, particle properties, indirect detection breakthrough. The center may uniquely favor such remnants. Tidal interactions disrupting binaries, spin-up in crowded conditions, survival near the black hole, or dark matter's density cusp naturally produces the signal. Quiet questions recur. Why the lingering symmetry? Could conditions blend both explanations seamlessly? The thrill lies in the nuance. Science as living process, evidence shifting gradually. No forced conclusion, only deepening mystery. The debate sharpens with each data release. Upcoming instruments promise finer source resolution, spectral mapping at higher energies, distinguishing mechanisms definitively. Whether exotic particles or overlooked corpses, this phantom glow shares the center with another impossibility. Threads of plasma that stand impossibly straight amid chaos. The phantom glow does not exist in isolation. It shares the turbulent heart with the bubble's roots, the black hole's shadow. And another striking feature, long threads of radio emission rising vertically from the plane. These non-thermal filaments cluster within a few hundred light-years of the center, visible only in radio waves. Their proximity to the excess and bubbles invites connections, shared origins in magnetic fields amplified by past activity, or cosmic rays accelerated in the same events. Beside the phantom glow rise rigid strands that should bend or break, yet endure perfectly aligned. The center hosts layered anomalies delicately balanced, underfeeding, allowing outbursts carving cavities, and perhaps seeding pulsars or dark matter signals, unexplained light persisting amid chaos. Each defies simple resolution, yet coexists. Recent multi-wavelength correlations tie them tighter. Polarized radio maps show fields draped along bubble edges and filament lengths. X-ray features align with gamma boundaries. The excess's morphology overlaps bubble bases, suggesting injected cosmic rays or altered populations from the same epoch. A subtle revelation emerges. The center's mild activity permits these features to form and endure. In more violent nuclei, constant disruption might erase filaments, overproduce gamma rays conventionally, or prevent bubble inflation. The web forms hypnotically, the starving giant's restraint enabling focused releases, sculpting bubbles, organizing magnetism into threads, perhaps fostering conditions for the glow, whether stellar remnants or exotic annihilation. The interconnected anomalies paint a heart that beats slowly, episodic, regulated, preserving structure where violence should dominate. These straight threads pierce the turbulent heart like frozen lightning, structures no ordinary turbulence should allow to survive. These straight threads pierce the turbulent heart like frozen lightning, structures no ordinary turbulence should allow to survive. Shift now to radio wavelengths, where the galactic center reveals yet another impossibility. Within a few hundred light-years of Sagittarius A, scattered among swirling gas and brilliant young stars, rise long, narrow strands visible only in radio emission. Discovered in the 1980s during wide-field surveys, these non-thermal filaments stand out starkly against the chaotic background. Strikingly linear, extraordinarily slender. Some extend more than 100 light-years in length, yet remain only a few light-years wide. They rise almost vertically from the plane, like rigid bristles defying the wild environment around them. The central region is the galaxy's most violent metropolis. Gas clouds collide at high speed. Supernova shocks ripple outward. Massive stars flood the area with radiation and winds. Magnetic fields twist in turmoil. Ordinary plasma threads should bend, fragment, or diffuse under such forces. Yet these filaments endure remarkably straight, as if held taut by unseen hands. Their emission comes from synchrotron radiation, electrons spiraling along powerful magnetic fields at nearly light speed. The fields within the threads reach strengths far above the galactic average, organized parallel to their lengths. Polarization maps show this alignment clearly, orderly, where chaos reigns. Many filaments cluster in bundles, running parallel like harp strings. Others stand solitary, piercing through dense molecular clouds without deviation. Their bases often anchor near the plane, extending outward into the halo transition. In the galaxy's wildest region stand perfectly straight threads of plasma, defying every force that should twist or tear them. Visualize them as frozen lightning captured mid-flash, rigid, luminous in radio eyes, cutting through the storm unscathed. Early images from the Very Large Array revealed them as isolated curiosities. Higher resolution with Jansky VLA and Meerkat sharpened the picture. Faint substructure, gentle curves in some, but overall linearity preserved. No comparable concentration exists elsewhere in the Milky Way. A few shorter, fainter threads appear in spiral arms, but the central ones dominate, longest, straightest, most numerous. The anomaly deepens with context. Turbulence in the central molecular zone should shear any elongated structure rapidly. Shocks from supernovae or cloud collisions should disrupt alignment. Yet the filaments persist, some for millions of years based on energy estimates. They illuminate only where cosmic rays, vast particles, interact with the strong fields. The threads themselves may be common, lit up brightly here by the extreme environment. Many of these threads point accusingly toward the black hole itself. The filaments invite speculation, origins as mysterious as their persistence. One interpretation links them directly to Sagittarius R. In its more active past, outflows or jets may have channeled magnetic fields outward, creating flux tubes that particles illuminate today. The alignment supports this. Many threads converge toward the black hole's position, as if anchored there. Their vertical orientation matches expected jet directions perpendicular to the disk. Yet the black hole shows little current activity capable of maintaining them. Not all filaments point precisely. Some run parallel or at angles. Another view sees them as amplified galactic magnetic fields. The Milky Way possesses an organized component running along spiral arms. In the center, turbulence and sheer stretch and strengthen field lines into long tubes. Cosmic rays trapped within then produce the synchrotron glow. High-resolution images from Meerkat reveal exquisite detail, gentle helical twists winding along lengths, faint connections to supernova remnants or molecular outflows. Some threads appear to transport energy upward, perhaps feeding the Fermi bubbles. A striking revelation emerges from wider surveys. Solitary filaments now appear far from the center, in spiral arms near the sun's position, even in the outer disk. These distant examples are shorter, fainter, less organized, but their existence suggests the phenomenon is galaxy-wide. The central threads are simply the most extreme, amplified by density, turbulence, and cosmic ray abundance unique to the heart. Polarization studies add another twist. Magnetic fields within threads exceed what surrounding pressure should allow. They resist compression, maintaining strength against the violent environment, implying continuous replenishment or extraordinary stability. What if these rigid strands are not local oddities, but traces of an invisible magnetic skeleton threading the entire Milky Way? The galaxy-wide distribution reshapes understanding. Differential rotation, cloud collisions, supernova feedback, all may stretch fields locally. In quieter regions, illumination is weak. Near the center, conditions conspire to make them dramatic. Recent models propose the threads as illuminated edges of larger flux tubes, part of a pervasive magnetic web organizing gas flow, influencing star formation, channeling cosmic rays. Their straightness reflects tension in the field, like strings under pressure. As of early 2026, multi-wavelength views refine the picture. Very long baseline interferometry resolves substructure showing braided fields. Connections to X-ray features hint at heating mechanisms. The filaments reveal magnetism's overlooked role, not mere byproduct, but architect maintaining order amid chaos. They stand as evidence of forces balancing the center's violence, perhaps enabled by the black hole's restraint. While the threads organize magnetism, nearby objects approach the black hole too closely, and somehow survive forces that should shred them utterly. The radio filaments rise from the same extreme environment, hosting the bubbles, the excess, the starving giant, a region where anomalies cluster densely. This crowded heart permits fragile structures to persist, threads enduring turbulence, bubbles preserving sharpness, excess glowing softly. The black hole's mild feeding may play a role, lacking constant disruption from powerful accretion, allowing organized features to form and survive. Closer still to the event horizon, in the frantic S-cluster, where stars whip at incredible speeds, another impossibility drifts among them. Compact infrared sources, labeled G1 through G6, follow highly eccentric orbits, approaching within a few hundred astronomical units of the black hole. At closest passage, tidal forces reach extremes capable of spaghettifying ordinary objects. Closer to the event horizon, drift dusty wanderers that stretch like taffy, yet return intact. These wanderers behave strangely. During pericenter, they elongate dramatically, stretching into thin filaments along their paths. Dust heats, brightness flares in infrared, yet they do not disintegrate completely. After passage, they gradually recompress, rounding out to continue their orbits. G2's 2013 to 2014 approach drew intense scrutiny. Predictions of total disruption unmet. It lengthened, brightened, trailed faint material, but survived largely coherent. Newer objects repeat the pattern, stretching under tides, enduring where loose gas should scatter. The shared environment ties anomalies together. The black hole's restraint leaves room for such fragile dancers. Past activity may have delivered their material, debris from disrupted systems or clouds. Magnetic threads nearby perhaps influence their paths or stability. The center maintains delicate equilibrium, violence tempered, allowing straight filaments, surviving imposters, preserved bubbles. Each feature defies expectation yet coexists, painting a heart more organized than its chaos suggests. These imposters orbit where nothing fragile should endure, masquerading as stars while tides test their true nature. These imposters orbit where nothing fragile should endure, masquerading as stars while tides test their true nature. Draw even closer now to the black hole's immediate domain, the S-cluster, a frantic swarm of stars locked in tight, elliptical paths around Sagittarius A. Here, gravity rules with absolute authority. Orbits complete in mere decades or years. Speeds reach staggering fractions of light itself. Among these ordinary stars drift objects that do not belong. Labeled simply G1 through G6, they appear as compact infrared sources, faint, dusty, unassuming when far out on their orbits, but their paths are highly eccentric, plunging perilously close to the event horizon at pericenter. Within a few hundred astronomical units, roughly the scale of our outer solar system. At such distances, tidal forces become monstrous. Gravity's gradient stretches anything extended, pulling harder on the near side than the far. Loose gas clouds should spaghettify completely, elongated into streams, disrupted beyond recovery, feeding the black hole in a brief glow. Yet these wanderers behave differently. G1 was spotted first in the early 2000s, its orbit tracked over years. During observed closest approaches, it elongated slightly, brightened in dust emission, but held together. G2 drew worldwide attention around 2011-2014. Predictions ranged from mild disturbance to total shredding and dramatic accretion flare. Telescopes watched intently as G2 approached. In the months before pericenter, it began to stretch, lengthening along its orbital path into a thin filament. Dust heated, infrared brightness rose. The object trailed faint material, appearing disrupted. The black hole remained quiet. No major flare announced a large meal. After passage, G2 gradually recompressed, rounding out over years, dimmer now but recognizable, continuing its long orbit. Newer discoveries repeated the pattern. G3 through G6, identified progressively from 2019 to 2024, with improving adaptive optics, follow similar tight, eccentric paths. Each approaches within hundreds of AU, stretches noticeably during pericenter, brightens in specific wavelengths, then recovers on the outbound leg. Objects skimming the black hole's edge should be ripped apart forever. Yet some round up and return. These events unfold on human time scales, pericenters separated by decades, offering rare real-time drama in cosmic terms. Unlike ancient bubbles or persistent waves, the G objects allow direct observation of tidal extremes in action. Their masses, inferred from orbital influence, range from a few Earth masses to perhaps Jupiter scale, too low for self-sustaining fusion, too coherent for simple debris. Infrared spectroscopy reveals broad emission lines from hot gas and dust, suggesting outflowing material. Yet compactness far from pericenter implies bound structure. The anomaly sharpens. Tidal forces at closest approach exceed what loose clouds should withstand repeatedly. Some objects have completed multiple observed passages with minimal loss. The S-cluster environment adds hostility. Intense radiation, winds from massive stars, frequent close encounters. Fragile interlopers should evaporate or disrupt long before reaching pericenter. Yet they persist, stretching like taffy under gravity's pull, then resiliently reforming. Their persistence challenges every expectation of tidal destruction. The survival of these tidal imposters has spawned competing explanations, each struggling to account for their repeated endurance. The leading view casts them as dusty gas clouds, perhaps remnants of disrupted protoplanetary disks around young stars or tidal debris from earlier encounters. Thick dust envelopes shield cooler gas within from radiation and winds. During pericenter, tides stretch the envelope dramatically, heating dust and producing observed brightening. Magnetic fields or self-gravity pull material back together afterward. This cloud model matched early G2 predictions well. Simulations showed compact, dusty clouds could elongate without total disruption, explaining the lack of strong accretion flare. Broad emission lines from spectroscopy support it. Signs of outflowing gas, no clear stellar features. Yet longevity challenges the idea. Repeated passages should erode clouds gradually through evaporation or stripping. G1, tracked over multiple orbits, remains surprisingly compact at apocinter. Newer objects show similar resilience, losing little mass per pass. Are these survivors' clouds clinging desperately, or disguised stars that fused under pressure? The alternative proposes hidden bound cores, merged binary stars enveloped in thick dust shells ejected during coalescence. Picture-tight stellar pairs spiraling together over time, through gravitational waves or cluster interactions, fusing into a single bloated object surrounded by expelled material. From afar, it appears dusty and faint, mimicking a cloud. At pericenter, tides stretch the envelope dramatically, but the central merged star remains gravitationally bound, ensuring survival. The shell settles back afterward, ready for the next orbit. This binary merger scenario gained support around 2018 to 2020, especially for aligned orbits suggesting common origin, perhaps a binary disrupted by the black hole long ago, leaving dusty remnants. Latest infrared spectroscopy from Gravity and Osirini through 2025 reveals mixed signatures. Some objects show double-peaked lines hinting at rotation or bipolar outflows, consistent with a central object driving winds. Others display symmetric, cloud-like profiles. Hybrid ideas emerge, young stellar objects with massive disks, or post-merger stars still shedding envelopes. Polarimetry hints at organized magnetic fields aiding cohesion. Upcoming pericenters for remaining objects, combined with James Webb mid-infrared monitoring, promise finer details. X-ray searches may catch subtle feeding if hidden cores contribute. The ongoing saga captivates. Real-time tests of tidal physics, general relativity at extremes, stellar evolution in harshest conditions. Whatever their nature, the G objects highlight the center's delicate state. The black hole's restraint leaves space for such dances. Past activity may have delivered them, final debris from ancient disruptions finally arriving. The imposters bridge intimate and galactic scales, human time-scale drama echoing billion-year processes. Beyond the center's intimate anomalies, the disk itself hosts features that time should have erased. The G objects represent the most intimate anomalies, surviving where theory demands destruction. Yet their persistence fits the broader pattern, a center unusually calm, permitting fragile or transient features to endure. This tempered violence extends outward into the disk, where larger structures defy expectations of dissolution. Pull back from the S-cluster's frantic orbits to the sweeping spiral arms that define the Milky Way's beauty. These arms trace density waves, gentle compressions guiding gas into star-forming rivers. Over billions of years, differential rotation. Inner stars orbiting faster than outer should wind them tightly. Material near the center completes laps quickly, shearing patterns into tight coils or dissolving them entirely. Yet the arms remain gracefully open, well-defined, loosely wound, as if recently formed. The Milky Way's graceful arms should have tangled into chaos billions of years ago, yet remain elegantly open. Classic spiral galaxies often show tighter winding with age. Simulations of isolated disks predict rapid tangling, arms merging into rings or fading into featureless expanse within a few rotations. Our galaxy has completed dozens of cosmic years, the Sun's orbital periods around the center. Shear should have erased distinct arms long ago. Mechanisms maintain them, the central bar driving resonance, transient waves recurring rather than persisting, satellite interactions refreshing patterns. Yet the openness persists anomalously, sharper, more defined than many similar galaxies. The winding resistance connects to central restraint. A more active nucleus might drive stronger winds, disrupting arm coherence. Past outbursts like bubble inflation could have influenced gas distribution without total destruction. The disk preserves structure where time should erode it, much like filaments enduring turbulence, bubbles preserving edges, G-objects surviving tides. This winding dilemma hides a deeper persistence, arms that refuse to tighten despite relentless rotation. This winding dilemma hides a deeper persistence, arms that refuse to tighten despite relentless rotation. Pull back now from the crowded, violent heart and its intimate impossibilities. Let your gaze sweep outward across the vast disk that contains nearly all the Milky Way's stars. Here, the galaxy reveals its most iconic feature: graceful spiral arms curving gently from the central bulge, tracing rivers of gas and young stars across tens of thousands of light years. These arms are not solid bars of material. They are density waves, subtle compressions traveling through the disk like ripples on a pond. Gas clouds entering the wave, slow and bunch, cooling to ignite new stars that illuminate the pattern. The arms glow blue with hot, massive suns, contrasting the older, redder inter-arm regions. Seen from afar, in images of other galaxies or artistic reconstructions of our own, the spirals appear elegant, loosely wound, almost freshly formed. Yet the Milky Way is ancient. The disk settled billions of years ago. The Sun has completed more than 20 orbits around the center since its birth. Differential rotation rules relentlessly. Stars closer in move faster, completing laps quickly. Those farther out drift more slowly. This shear should wind any fixed pattern tightly over time. Material arms would coil like a spring, merging into rings or dissolving into uniformity within a few rotations. Density waves, too, should wrap densely, losing definition. Our galaxy's beautiful spirals should have coiled into a featureless disk long ago. Simulations of isolated disks confirm the expectation. Spiral patterns emerge early from instabilities, but shear tightens them rapidly. Within 1 billion years, a mere fraction of cosmic history, distinct arms fade, leaving smooth or barred structures. Yet the Milky Way preserves well-defined open arms. 4 major ones: Scutum Centaurus, Sagittarius, Orion, Perseus, plus minor spurs, loosely wound with pitch angles around 15 to 20 degrees. Infrared maps from Spitzer and radiohydrogen traces from decades of surveys outline them clearly, even through dust. The anomaly persists across comparisons. Many spiral galaxies show tighter winding or grand design pairs driven by companions. Our arms remain multi-armed, flocculent yet organized, sharper than age alone allows. Quiet questions arise. What prevents the inevitable tangling? How do the arms maintain openness against billions of years of shear? The pattern feels almost deliberate, preserved where time should erase it. Like filaments enduring turbulence or G-objects surviving tides, the arms defy dissolution. The disk remembers its youth vividly, tracing patterns that should have blurred into oblivion. Something maintains their openness. The persistence of open spirals has long puzzled astronomers. Several mechanisms conspire to delay or prevent winding, each partial yet collectively compelling. The central bar plays a key role. Extending from the bulge, it rotates as a solid unit, driving resonance that sustains 2 primary arms at its ends. Density waves couple to the bar's pattern speed, maintaining coherence against shear. Beyond the bar, additional arms may arise from instabilities, self-propagating star formation or swing amplification at the disk's edge. Satellite galaxies like the Magellanic Clouds or past encounters can excite transient patterns, refreshing arms periodically. Simulations incorporating these effects show spirals lasting longer, but often still winding or fragmenting over Geiger years. Multi-armed patterns emerge naturally, yet openness requires ongoing regeneration. A deeper revelation reshapes the picture. The arms we see may not be ancient survivors, but recurring transients, temporary illusions reborn repeatedly from underlying chaos. Modern models favor this view. Spiral arms are not permanent material structures or fixed waves, but short-lived features, lasting a few 100 million years before dissolving, then reforming elsewhere from fresh instabilities. The bar maintains grand design arms near the center. Farther out, stochastic processes, cloud collisions, feedback from dying stars, minor perturbations, seed new segments constantly. Satellite passages add kicks, exciting modes that propagate as visible arms. Gaia data through 2025 supports recurrence. Proper motions reveal arms as overlapping segments with varying pattern speeds, not a single coherent wave. Chemical abundances show young stars in arms born recently, not carried along fixed paths. The arms we see today may be temporary illusions, reborn repeatedly from chaos. This transient nature resolves the winding paradox elegantly. No single pattern endures long enough to tighten fatally. Shear disperses one generation. New ones emerge before the disk smooths completely. The recurrence feels almost rhythmic, the disk breathing patterns in and out over cosmic seasons. Feedback from star formation self-regulates. Compression ignites stars, their supernovae, and winds disperse gas, clearing space for the next wave. Connections to central anomalies deepen. The black hole's restraint avoids strong winds that might quench arm formation galaxy-wide. Past outbursts like bubbles could have influenced gas distribution without erasing structure. The multi-armed flocculent appearance fits recurrence, messy, overlapping segments rather than perfect grand design. The disk maintains beauty through renewal, not eternal preservation, but continual rebirth. Patterns dissolve and reform, openness sustained by impermanence. The view shifts perspective. What appears stable is dynamic. What seems ancient is recent. The spirals captivate precisely because they are ephemeral on galactic scales. Even the disk's vertical calm hides unlikely waves. The spiral arms trace horizontal patterns defying time's shear through renewal. Yet the disk harbors vertical anomalies equally persistent, oscillations that gravity should damp quickly. Withdraw farther from the center, past the bar and major arms, to the sun's quiet neighborhood in the Orion Spur. Here, between Sagittarius and Perseus arms, a vast undulation reveals itself in three-dimensional maps. Combining Gaia distances with dust extinction models since 2019 to 2020, uncovered the Radcliffe Wave, a sinusoidal ripple of gas and young stars stretching nearly 9,000 light-years along the local arm. It rises and falls hundreds of light-years above and below the midplane, connecting star-forming regions like Orion, Perseus, and Cygnus into one coherent structure. The Sun sits near a crest, roughly 500 light-years above the average plane, looking slightly downward toward the center. A vast ripple through our local arm should have flattened, yet oscillates still. Gravity acts to restore the disk's flatness. Vertical motions should damp rapidly through collisions and energy dissipation within tens of millions of years. Yet the wave maintains amplitude and coherence, velocities aligned along its length. Mass involved equals millions of suns moving together as if disturbed recently. Simulations predict quick settling unless continuously driven or unusually resilient. The persistence feels personal. The ripple cradles our solar system, perhaps influencing comet orbits or past gas distribution. Star-forming crests host the nurseries we admire. Troughs remain quieter. The wave records a blow delivered long ago, a kick whose echo endures against expectation. Causes point outward, passage of the Sagittarius dwarf galaxy, grazing the disk tens of millions of years ago, or a dark matter subhalo crossing undetected. Both could excite large vertical modes. Recent Gaia refinements through 2025 show the wave still oscillating. Not a static fossil, but dynamically alive, damping slower than predicted. Magnetic tension or ongoing minor perturbations may sustain it. The undulating veil connects to spiral renewal. The same satellite interactions refreshing horizontal arms could excite vertical ones. Central restraint avoids disruption that might flatten everything. The disk preserves memory vertically as horizontally, patterns persisting where physics demands erasure. This undulating veil records ancient impacts whose debris orbits far beyond. This undulating veil records ancient impacts whose debris orbits far beyond. Leave behind the graceful recurring spirals and descend gently into the sun's own neighborhood, the quiet interarm region known as the Orion Spur. Here, in the part of the galaxy we call home, a vast vertical oscillation reveals itself only in three-dimensional maps. Discovered through combined Gaia distances and dust modeling in 2019 to 2020, it stretches nearly 9,000 light-years along the local arm, a sinusoidal wave of dense gas and young stars rising and falling hundreds of light-years above and below the midplane. Famous star-forming regions, Orion Nebula, Perseus Clouds, Cygnus Rift, Scorpius-Centaurus Association, align along its crests and troughs, connected into one coherent structure for the first time. They are not scattered randomly but sit upon the same gentle swell. The wave undulates like a frozen ocean ripple captured in slow motion. The sun itself rests near a crest, approximately 500 light-years above the average galactic plane, gazing slightly downward toward the distant center. The arm we live in rises and falls like a frozen ocean swell, a wave that gravity should have erased millions of years ago. Gravity works relentlessly to flatten the disk. Stars and gas feel a restoring force, pulling them back toward the mid-plane whenever displaced. Collisions and energy dissipation should damp vertical motions quickly. Within tens of millions of years, a mere heartbeat in cosmic time. Yet the Radcliffe wave maintains remarkable amplitude and coherence. Velocities align along its length, upward on one slope, downward on the other, oscillating together as a unified mode. Its mass equals millions of suns, all moving in concert. Early two-dimensional maps hid it completely. The galaxy appeared flat, vertical deviations minor and chaotic. Only precise distances from Gaia peeled away the projection, revealing the hidden dimension. The structure feels intimate. The Orion Nebula, visible to naked eyes on winter nights, sits near a crest. The Pleiades and Hyades clusters trace its path. Comets in our Oort cloud may feel subtle gravitational tugs from its passage. The wave cradles the solar system gently, perhaps influencing past gas flows or planetary migrations. Its persistence defies simple damping, as if the initial disturbance happened recently, or something resists gravity's pull. Quiet questions surface. How can such massive, organized motion endure? What preserves coherence against inevitable settling? The ripple stands as another defiance, pattern persisting where physics demands erasure. Like open arms renewed recurrently, or filaments enduring turbulence, the wave refuses to flatten. It records a blow delivered long ago, an impact whose echo lingers vividly. What kick launched this enduring ripple? The Radcliffe wave did not arise gently. Something struck the disk powerfully tens of millions of years ago, exciting a large vertical mode whose oscillation persists against expectation. Leading candidates point to external perturbers. The Sagittarius dwarf spheroidal galaxy, a small companion currently being torn apart, has plunged through the disk multiple times in its orbit. Simulations show such passages can bend the plane like a drumhead struck off-center, launching waves that propagate outward. One earlier crossing, roughly 50 to 100 million years ago, aligns with the wave's estimated age and orientation. Yet the fit is imperfect. The wave's length and amplitude require a specific impact angle and mass. Recent modeling through 2025 suggests Sagittarius alone may not suffice. Additional disturbances or internal amplification needed. Another possibility invokes invisible actors, a dark matter subhalo passing through the disk near our position. The halo should contain thousands of such clumps, remnants of early formation, massive enough for gravity to excite waves without visible traces. A subhalo of several million solar masses crossing at the right velocity could tug gas and stars upward and downward coherently. This dark perturber appeals because it leaves no stellar debris, matching the wave's clean, gas-dominated structure. No bright companion marks the event. Central origins have been proposed, pressure waves from past black hole outbursts, like those inflating bubbles, propagating outward and bending the disk far away. Though weakened by distance, focused energy could imprint vertical motions. The ripple still moves, as if the blow landed only yesterday in cosmic terms. Refined Gaia data releases through 2025 deliver the striking revelation. The wave is not a static fossil, but dynamically oscillating. Vertical velocities remain coherent and significant along its length, upward motion on rising slopes matching downward on falling ones. Damping has proceeded slower than standard models predict. Magnetic fields threading the gas may provide tension, like strings resisting relaxation, or ongoing minor perturbations, smaller satellite brushes or internal instabilities, feed energy subtly. The ongoing motion deepens the anomaly. Most vertical disturbances in simulations settle quickly, leaving faint warps at best. Here, the wave endures vividly, perhaps amplified by the disk's self-gravity or gas pressure. The violent origin contrasts the gentle appearance, a cosmic graze producing a serene swell we live upon. The impact reshaped local structure without catastrophic disruption. Moderated violence creating lasting pattern. Connections ripple inward. The same restraint permitting central anomalies may allow distant echoes to preserve. A more active nucleus might drive winds flattening everything. The wave personalizes the galaxy's history. Our quiet neighborhood bearing subtle scar from ancient turmoil. Those impacts left permanent scars in the halo. The Radcliffe wave captures a transient memory, a vertical oscillation excited by ancient impact, persisting longer than expected, but destined to fade eventually as gravity restores flatness. Yet the same disturbances that launched the ripple-stripped stars from passing satellites, scattering them into long-lived orbits high above and below the plane. These stellar streams wrap the galaxy multiple times, preserved in the low-friction halo where damping is minimal. Gaia's precise motions have revealed dozens, thin rivers of stars sharing chemistry and velocity, betraying common origins in devoured companions. Major mergers like Gaia Sausage Enceladus dominate the inner halo with highly eccentric orbits. Smaller accretions leave fainter threads, Sequoia, Kraken, Helmi streams. The ongoing Sagittarius disruption loops visibly around us. The Milky Way should swarm with thousands of dark companions, yet hosts far fewer than theory demands. Cold dark matter hierarchy predicts abundant subhalos, from dwarf galaxy scales down to tiny clumps. Many should host visible satellites, orbiting as luminous dwarfs, yet surveys find only about 50 around the Milky Way, far short of hundreds expected. The missing satellites paradox has persisted for decades. Ultra-faint discoveries ease it slightly, but the discrepancy remains stark. Most subhalos should be dark, too small or stripped to form stars, yet their gravity should still perturb streams and disk. The wave and streams intertwine. The same Sagittarius passages exciting local oscillation scattered its stars into the prominent stream. Other ripples in the disk, smaller waves mapped by Gaia, trace additional impacts whose debris populates the halo. The disk records transient blows vertically. The halo preserves permanent debris horizontally. Both reveal ongoing accretion, moderated rather than catastrophic. Central calm connects again. A more violent nucleus might disrupt satellites earlier or prevent wave excitation. Restraint allows echoes to endure. The missing satellites challenge dark matter's small-scale behavior. Perhaps warmer particles, self-interactions, or altered formation reducing subhalo abundance. The paradox bridges visible and invisible. Stellar streams as fossils of seen mergers, absent subhalos as ghosts of unseen ones. This missing satellites paradox challenges the universe's foundational scaffolding. This missing satellites paradox challenges the universe's foundational scaffolding. Ascend now from the rippling disk and its persistent waves into the vast, faint halo that envelops everything. A spherical envelope extending hundreds of thousands of light years, filled mostly with ancient stars, globular clusters, and the invisible substance we call dark matter. In the standard cosmological picture, dark matter formed the first structures. Cold and slow-moving, it clumped early under gravity, building a hierarchy of halos within halos. Large galaxies like the Milky Way grew by merging these smaller building blocks, inheriting thousands of subhalos, remnants orbiting within the main halo. Many subhalos should host visible dwarf galaxies, shining with their own stars. Others, smaller or stripped, remain dark, detectable only through gravity. Theory predicts abundance. Hundreds of luminous satellites, thousands of dark clumps ranging down to millions or even lower masses. Yet surveys reveal scarcity. Around the Milky Way, we have identified roughly 50 dwarf companions, bright ones like the Magellanic Clouds, ultra-faint ones discovered in recent decades. The count falls far short of expectations. Our galaxy should be orbited by thousands of invisible clumps, but most are mysteriously absent. The missing satellites problem emerged decades ago, as simulations outpaced observations. Deeper searches with telescopes like DES and Subaru eased it slightly, uncovering dozens of ultra-faints too dim to spot earlier. Yet the gap persists. Observed dwarfs number far fewer than luminous subhalos predicted. Dark subhalos should outnumber them vastly, betraying presence through gravitational tugs on streams or disk warps. Indirect signs remain tentative. The paradox probes dark matter's nature deeply. Cold dark matter hierarchy produces rich small-scale structure naturally. Scarcity suggests alternatives, warmer particles moving faster, suppressing tiny clumps, self-interacting dark matter smoothing distribution, or modified gravity reducing subhalo survival. Baryonic physics offers partial rescue. Supernova feedback or rayonization heating gas in small halos, preventing star formation and rendering many dark. Tidal stripping by the Milky Way disrupts fragile ones, yet even accounting for these, simulations still overproduce visible dwarfs compared to observations. The discrepancy sharpens on smallest scales. Subhalos below 10 UL8 solar masses should swarm, yet perturbations remain subtle. The halo appears smoother than expected, substructure suppressed somehow. Quiet questions linger. Did early universe conditions differ? Does dark matter behave unexpectedly on small scales? Or have we missed faint satellites hiding in plain sight? The vanishing clumps challenge cosmology's foundation, the cold, collisionless paradigm underpinning structure formation across the universe. If resolved by baryonic effects, the model survives strengthened. If fundamental, new physics beckons, the search continues patiently. Wider surveys, deeper imaging, precise motions from Gaia. Each new dwarf, or lack thereof, refines the puzzle. Indirect hunts reveal faint hints. Direct counts fall short, but gravity leaves traces even invisible clumps cannot hide. Stellar streams, those thin rivers of accreted stars wrapping the halo, serve as sensitive detectors. Long and cold in velocity space, they flow smoothly along predicted orbits. A subhalo passing nearby tugs stars aside, creating gaps, spurs, or density variations. Gaia's exquisite precision has turned streams into gravitational minefields. The most famous case remains GD1, a narrow, ancient stream stretching across the sky. Maps reveal a clean gap on one side, matched by a spur of offset stars on the other, as if an unseen mass brushed past, scattering material into parallel track while thinning the main flow. Simulations match beautifully. A subhalo around 10 8 solar masses, crossing at suitable speed and angle, produces exactly this signature. No visible counterpart exists, no dwarf, no cluster. Palomar 5's tidal tails show wiggles and underdensities consistent with multiple encounters. Recent analyses flag sharp gaps aligned with velocity shifts. Newer streams add candidates. Orphan Chenab displays subtle variations, Jalem an offset branch, Phoenix a density drop. Statistical studies across dozens combine to estimate perturbation rate. Tiny gaps in stellar rivers may mark ghosts we cannot see. As of early 2026, detections accumulate weight. Machine learning scours Gaia phase space for anomalies, flagging several high-confidence gap-spur pairs best fit by dark perturbers. Masses cluster around 10, 7, 10 to 9 solar masses, probing scales inaccessible elsewhere. Not every feature proves subhalo. Internal dynamics or known interactions can mimic, but the cleanest cases resist alternatives, their geometry too precise for coincidence. The excitement lies in indirect power, probing dark matter distribution without light. Rich perturbations support cold dark matter. Paucity favors suppression mechanisms. Disk warps and flares offer complementary hints. Vertical heating consistent with past passages. Hypervelocity stars flung outward may trace disruptions near the center. The vanishing satellites gain nuance through these ghosts. Many small subhalos may survive dark, stripped of baryons yet gravitationally active. Others destroyed entirely by tides. The halo's smoothness challenges yet intrigues, perhaps resolved by feedback, perhaps demanding new physics. The clues grow sharper, the web tighter, impacts exciting waves, scattering streams, leaving gaps where dark clumps passed silently. Recent years sharpen every anomaly. The missing satellites and their faint gravitational echoes form one piece of the interconnected puzzle. Yet the picture evolves rapidly, new observations refining every strangest feature. In 2025-2026, fresh data from ongoing missions and previews sharpened anomalies unexpectedly. Gaia's final processing and focused releases refined stream perturbations, adding statistical weight to subhalo candidates. Vertical disk maps extended the Radcliffe wave farther, revealing connections to smaller ripples, a hierarchy of oscillations defying quick damping. JWST deep infrared fields pierced central dust, resolving more stellar sources and tightening constraints on the gamma-ray excess. Erosita all-sky refinements outlined bubble edges with multiple shells, suggesting episodic rather than single outbursts. Meerkat and low-frequency arrays traced magnetic filaments galaxy-wide, revealing faint counterparts in arms, the central ones merely brightest examples. New Eyes in 2025 revealed features no model foresaw, subtle warps in outer disk aligned with predicted subhalo passages. Faint halo overdensities hinted at wrapped streams from minor mergers. Central flare monitoring caught more frequent mild events, underscoring episodic feeding. The surprises reframed anomalies as layered responses, central restraint permitting outflows and organized magnetism. moderated accretion allowing wave excitation and stream preservation, suppressed substructure consistent with observed calm. Features once isolated now interconnect visibly. Bubbles influencing halo gas, waves recording the same impacts, scattering streams, gaps marking missing clumps whose absence enables persistence. The galaxy emerges more dynamic yet balanced, violence tempered, patterns enduring where chaos should dominate. These surprises reframe the strangest features as interconnected, painting a portrait of unusual moderation that may explain our very existence. The unfinished map gains clarity, yet deeper shadows beckon, demanding tools not yet fully online to resolve why these impossibilities cluster in our home. Recent years sharpen every anomaly. The pace of revelation has quickened in ways no one fully anticipated. Throughout 2025 and into early 2026, a steady stream of new observations arrived from instruments long at work and others just beginning to flex their full power. Each dataset peeled away another thin layer, but instead of softening the strangest features, the fresh views made them stand out more starkly. Gaia, having completed its mission in late 2024, entered intensive processing for the 4th and 5th data releases. Early previews and targeted studies released through 2025 already carried weight. Refined proper motions exposed subtler substructures in the halo, faint phase space folds suggesting merger remnants previously blurred. Vertical velocity fields across the disk extended the Radcliffe wave's influence farther along the Perseus and Scutum arms, revealing a hierarchy of nested oscillations no simple impact model predicted. In the bulge, improved distances uncovered hidden stellar associations near bar ends, pockets where gas funneling appeared episodic rather than steady. The James Webb Space Telescope delivered penetrating infrared views that cut through dust like never before. Deep fields of the Central Zone, published in phases through 2025, resolved obscured star-forming complexes in exquisite detail. Sagittarius C emerged as a turbulent nursery, packed with protostars, yet strangely inefficient, echoing the central molecular zone's inhibited collapse on smaller scales. Spectroscopy caught brief, unexplained brightenings near Sagittarius A, mild flares suggesting infrequent accretion of small debris. Further out, JWST mapped embedded clusters along giant molecular filaments, revealing dense core chains glowing faintly in cooled dust. Reservoirs far more organized than random collapse should allow. Erosita's all-sky X-ray surveys reached deeper sensitivity by 2025, refining the Fermi bubble's hot interiors. Edges appeared not single but layered, fainter, cooler extensions surrounding the bright gamma-ray boundaries, hinting at multiple expansion episodes. Embedded cold clouds, mapped with radio follow-ups, proved more numerous and structured, some aligned in streams falling back toward the disk. Low-frequency radio panoramas from Murchison Wide-Field Array precursors assembled the widest color composite views yet, polarized emission outlining vast synchrotron loops and magnetic drapery across the plane and halo transition. Meerkat snapshots resolved central filaments into braided subthreads, while Skae pathfinders traced fainter counterparts in spiral arms, the rigid strands no longer unique, but most extreme at the heart. 2025's fresh maps turned mild puzzles into stark impossibilities. A colossal vertical wave, spanning tens of thousands of light years, gained clearer amplitude, defying damping timescales. Faint radio arcs high in the halo suggested relic outflows older than the bubbles. Stream perturbations aligned suspiciously with dark subhalo paths, their statistics tilting toward richer small-scale structure than smoothed models allowed. The surprises challenged predictions directly. Excess morphology sharpened, bubble phases multiplied, wave coherence deepened, filament networks expanded. Features once explained marginally now demanded revision. The galaxy appeared more restless, yet more organized, episodic violence layered precisely, persistence amplified rather than erased. Old anomalies gained new edges. The new observations did not merely add detail. They reshaped interpretations of every strangest feature, turning tentative explanations into strained ones. The gamma-ray excess felt the sharpest impact. Refined Fermi background subtraction, combined with JWST's resolved infrared sources, isolated more faint point candidates in the bulge. The excess's morphology tightened, slightly less spherical, with extensions tracing bar influence more clearly. Spectral softness at high energies favored millisecond pulsars further, yet the central bulbous core remained stubbornly symmetric, preserving room for a dark matter whisper. The Fermi bubbles gained complexity. Erosita's layered edges and embedded cloud streams suggested not one outburst, but several. Older, larger cavities overlaid by the bright gamma lobes. Alignment remained exquisite, but energy estimates rose, challenging single-event models. The multiple phases tilted toward episodic black hole feedback, amplified perhaps by stellar contributions. Radio filaments expanded in scope. Galaxy-wide, faint counterparts showed the rigid strands as common. Local turbulence stretching fields everywhere, illuminated brightly only where conditions peak. Central extremes sharpened, helical twists, connections to outflows, polarization indicating fields resisting compression unnaturally. The Radcliffe wave extended and deepened. Nested smaller ripples appeared within, velocities more coherent than damping allows. The structure connected to broader disk breathing. Vertical modes excited hierarchically, persisting through magnetic tension or continuous feeding. Features we thought understood now evolve before our eyes. Spiral arms gained transient segments with varying speeds, reinforcing recurrence over permanence. Stream gaps multiplied statistically. Subhalo masses clustering where suppression models predict scarcity. G-object monitoring caught spectral shifts, hinting at evaporating envelopes around bound cores. The anomalies interconnected visibly. Bubbles with phased histories influencing halo gas returned as falling clouds, waves recording impacts whose debris populated streams with gaps marking dark passers-by. filaments draping bubble surfaces while threading wave crests. The galaxy breathed on overlapping time scales. Million-year flares, 100-million-year oscillations, billion-year assembly, layered without mutual destruction. Central restraint emerged as enabler, mild feeding permitting focused outflows carving bubbles, organized magnetism into threads, inhibited collapse preserving gas for waves. Moderated accretion avoided disruption flattening everything. The strangest traits sharpened into pattern. Persistence where erasure expected, order amid potential chaos, calm enabling subtle violence. The living galaxy revealed, not static portrait, but evolving organism. Anomalies as vital signs of unusual equilibrium. Future tools will clarify further. The sharpened anomalies of 2025-2026 hover at detectability's edge. Streams faint, perturbations subtle, obscured cores teasing. Many secrets demand capabilities only now approaching. Within the coming decade, a new generation of observatories promises to illuminate the strange features with unprecedented breadth and depth. The Nancy Grace Roman Space Telescope, launching as early as 2027, will sweep wide-field infrared surveys across plane and bulge. Its micro-lensing program will probe billions of stars for hidden wobbles, revealing faint halo members and free-floating objects. Deep bulge fields will census obscured populations precisely, distinguishing accreted from native stars, clarifying bar-driven dynamics influencing arms and excess. The Vera C. Rubin Observatory, entering full operations around 2027, will transform ground-based time domain viewing. Its legacy survey of space and time will image vast skies repeatedly, catching transients from disk to halo. Variability and motions paired with spectroscopy will map streams in detail, hunt subhalo perturbations in real time, trace wave evolution through stellar tracers. The full square kilometer array, phased in through late 2020s and 2030s, will revolutionize radio. SKA-LO will detail hydrogen and synchrotron across halo, mapping relic outflows and magnetic drapery. SKA-MID will resolve central pulsar candidates en masse, potentially settling the excess, while tracing filaments galaxy-wide with polarization unmatched. Extremely large ground telescopes, European ELT, 30-meter, Giant Magellan, will bring spectroscopic precision to crowded fields. Adaptive optics and multi-object capabilities will dissect halo stream chemistries. Fingerprint progenitors measure velocities near black hole for G-object orbits and relativity tests. Successor X-ray missions will map hot halo gas and bubble phases with greater sensitivity. Next-generation gamma facilities like Cherenkov Telescope Array will probe excess spectrum at extremes, distinguishing annihilation from astrophysical emission. Soon we may resolve why these strange features endure. The instruments will overlap synergistically. Roman's infrared census with Rubin's optical transients, SKR's radio continuity with ELT spectroscopy, Multi-messenger hints from LISA detecting intermediate black holes in streams or neutrinos signaling dark processes. The payoff could transform understanding. Complete dynamical map from filaments to outer substructure. Merger timelines dated precisely. Feedback cycles quantified. Small-scale dark matter tested rigorously. We may watch next G-object passages in exquisite detail, trace wave damping or refreshment, catalog filament networks fully. Count subhalos by gaps confidently. The galaxy's breathing will become visible. Inhale of gas, episodic exhales, settling of scars moderated. Hope rises naturally. For the first time, tools match the scale of questions, promising to explain why persistence dominates where erasure should. Why calm enables the strange endurances we have traced. Yet some anomalies may define our galaxy's unique character forever, traits not fully resolvable, marking the Milky Way as unusually gentle among cosmic violence. Yet some anomalies may define our galaxy's unique character forever. We have journeyed together through the strangest features the Milky Way guards most closely. A supermassive black hole that starves amid plenty, colossal cavities inflated by ancient violence, yet preserved sharply, a phantom glow refusing clear explanation, rigid plasma threads enduring chaos, tidal imposters surviving impossible stretching, spiral arms remaining open against relentless shear, a vast local ripple oscillating far longer than gravity allows, and dark satellites mysteriously absent despite predictions. Recent observations have only deepened these impossibilities, sharpening edges, revealing layers, connecting what once seemed separate. Step back now and consider the pattern that emerges. Every impossibility we've met suggests the Milky Way is unusually calm, perhaps uniquely so. The starving giant at the center feeds sparingly, its restraint permitting focused outflows that carve bubbles without constant disruption. Those bubbles preserve crisp boundaries and embedded clouds, echoes of episodic rather than relentless energy release. The phantom glow persists softly, whether from overlooked remnants or subtle new physics, neither dominating violently. Filaments stand straight where turbulence should shred them, organized magnetism resisting collapse. G-objects stretch and reform, surviving tides that demand destruction. Fragile dancers allowed space in a tempered environment. Spiral arms renew gracefully rather than tangle fatally. Recurrence sustaining openness. The Radcliffe wave undulates vividly, damping delayed by tension or moderation. Stellar streams wrap preserved, their gaps hinting at subhalos, scarce where abundance expected. Restraint threads through everything. A more gluttonous black hole might drive winds quenching arms, flattening waves, erasing filaments. Constant violence could scatter streams, overproduce conventional gamma rays, prevent bubble inflation. Missing satellites and suppressed substructure imply moderated accretion, fewer disruptive passages preserving disk calm. Episodic central activity clears without sterilizing. The anomalies interconnect as signs of balance, violence present yet regulated, persistence where erasure anticipated, order amid potential chaos. The galaxy breathes slowly, inhaling gas patiently, exhaling occasionally in structured sighs, settling scars without catastrophic upheaval. This calm feels deliberate, almost protective. Features that shouldn't exist endure because extremes are tempered. The Milky Way maintains equilibrium where many galaxies tip toward frenzy or starvation. Comparisons sharpen the outlier status. Active nuclei blaze in similar spirals. Tighter arms wind in older disks. Stronger substructure perturbs in simulations. Our home defies these norms subtly yet consistently. The interconnected restraint paints a portrait, a mature galaxy that grew through mergers yet settled gently. Its center dormant enough to allow subtle dynamics, its halo smooth enough to avoid constant disturbance. These features may explain our existence, a quiet cradle where complexity could emerge undisturbed. The gentle outlier status extends beyond one galaxy, touching cosmic context and philosophical depths. Among billions of spirals, how typical is this moderation? Supermassive black holes in similar masses often feed more actively, driving quasar phases or strong winds. Statistical samples place the Milky Way toward the quiet extreme. Its center's luminosity low even for quiescent systems. The restraint may be rare. Feedback cycles tuned to long, calm phases. Moderate merger history contributes. Major collisions like Gaia Enceladus occurred early, building mass without late chaos. Ongoing accretion, Sagittarius stream, missing smaller satellites, proceeds gently. Exciting waves and scattering debris without shattering disk stability. The stable disk favors life's prerequisites. Open arms sustain steady star formation without exhausting gas. Preserved reservoirs in filaments await measured release. Vertical calm and slow damping allow planetary systems to settle undisturbed. A more active center might expel metals needed for rocky worlds or irradiate zones lethally. Stronger substructure could fling planets from orbits through frequent passages. Tighter arms or flattened waves might concentrate supernovae dangerously. Our galaxy's strangest traits could be why we're here to wonder at them. The anomalies collectively enable habitability. Black hole restraint, preserving gas and chemistry. Episodic outflows clearing without sterilizing. Persistent patterns maintaining zones of relative peace. Suppressed disruption shielding solar systems. Philosophically, the gentle outlier resonates deeply. In a universe often violent, exploding stars, colliding galaxies, radiating nuclei, pockets of calm permit fragility. Complexity arises not despite chaos, but within moderated spaces. The Milky Way remembers its turbulent youth in streams and waves, yet settled into maturity, allowing thought to emerge. Its impossibilities, features defying violent norms, may be prerequisites for observers to notice them. Cosmologically, the traits test models. Rare quiet centers suggest feedback universality with varied outcomes. Missing satellites probe dark matter small scales, suppression favoring certain particle properties. Stable disks imply common paths to habitability. We inhabit not an average spiral, but one unusually suited for life. Its strangest features protective balances rather than threats. The deepest anomaly is the mystery itself. Why this moderation? Why here? Why allowing awareness of the wonder? The questions endure, pulling us onward. The galaxy guards some secrets not for concealment, but invitation, drawing minds to ponder the delicate equilibrium sustaining them. The Milky Way's calm outlier nature whispers. In vast cosmic violence, gentle spaces carve room for the fragile spark of curiosity. The deepest anomaly is the mystery itself. As our exploration draws to close, return once more to the beginning. A quiet night beneath open sky. Step outside, away from lights, and let your gaze settle on the faint river arching overhead. The Milky Way appears unchanged, a pale band guiding human wonder for millennia. Yet now you know the hidden layers within. The starving giant waits patiently at the heart, its restraint shaping everything. Ghostly cavities tower invisibly, preserving echoes of measured violence. Phantom light glows softly. Filaments stand rigid. Impostors dance at tide's edge. Arms renew gracefully. Waves undulate through our neighborhood. Streams drift with missing companions' ghosts. Recent sharpenings and future eyes will clarify much. Resolving glow's source, mapping subhalos, tracing waves' fate. The map grows ever finer, yet some shadows will linger. The deepest balances, why this moderation, why enabling life, may remain forever open, not resolvable, but resonant. The Milky Way's features that shouldn't exist may be exactly what allows us to exist. These anomalies, persistence against erasure, calm amid potential fury, form protective veils. They temper violence enough for chemistry to complexify, planets to stabilize, life to emerge and reflect. The galaxy cradles us gently, its strangest traits not threats, but guardians. The restraint that puzzles astronomers may have shielded zones where thought could arise undisturbed. Stand beneath the river of light, feel small against immensity, yet profoundly connected. The dust veiling once concealed, now it feels like gentle protection, preserving mystery in an era of revelation. Humanity's gaze pierces farther than ever, yet awe endures. Each answered question births deeper ones, the pull of wonder eternal. The map remains unfinished, as all true maps must. The Milky Way continues patient turning, breathing slowly, remembering ancient fire while nurturing fragile sparks. We, brief visitors within its disk, carry the mystery onward, awed by the gentle outlier that hosts us, drawn forever to the light, hiding so much yet revealing just enough. The answers may not arrive all at once, but the act of wondering changes us. If tonight's journey stirred something in you, let it settle gently. Thank you for listening. This has been the calm unknown. Rest well and keep wondering.